In this session, we are going to look at noise and denoising model. Noise introduction and denoising process are often used in machine learning, specifically in the domain of image and signal processing, but can be applied in other data types as well. The two primary components are noising and denoising. Noising is a model or function that intentionally adds noise to the data. It can be used to simulate real-world scenarios where data may be corrected by various sources of noise. For example, a noising model could add Gaussian noise to an image, simulating the effect of a poor quality camera sensor. This is commonly used in training to create robust models by augmenting the training dataset. Denoising model, on the other hand, is a model designed to remove the noise from the corrupted data and restore it as closely as possible to its original uncorrupted state. Denoising models are extensively used in image and signal processing to improve the quality of data. They can be designed using various techniques such as deep learning. When I say deep learning, we can use convolutional neural networks or autoencoders. We can also use wavelet transforms. One of the more common uses of these two is in the concept of denoising autoencoders. A denoising autoencoder is a specific type of neural network that is trained to remove noise from the corrupted data. During training, a noising function is applied to the input data, and the model learns to reconstruct the original uncorrupted data from the noisy input. This has been shown to improve the robustness and generalization of the model. In a broader sense, this concept is part of a larger theme in machine learning of training models to be robust against various forms of corruption in the data. Noise injection at training time can be seen as a form of data augmentation or as a form of regularizer, preventing overfitting by providing a harder training task. The denoising step then learns to recover from these specific corruptions, which can often generalize to unseen corruptions as well. Now let's look at Gaussian and speckle noise that are used in noising models. Gaussian noise, also known as white noise, is a type of statistical noise having a probability density function equal to that of a normal distribution, which is also known as the Gaussian distribution. In other words, the values that the noise can take on are Gaussian distributed or normally distributed. This means the noise in each pixel is independent of the color information in the pixel and is randomly spread throughout the data. In images, Gaussian noise tends to appear as speckles in otherwise smoothly colored regions and is typically caused by sensor noise and poor illumination. In the context of a noising model, adding Gaussian noise to an image might involve adding a random value drawn from a Gaussian distribution to the intensity of each pixel. This can make the model more robust to such noise in the real world. Speckle noise, on the other hand, is a granular interference that inherently exists in and degrades the quality of the active radar and synthetic aperture radar SAR images. Speckles are essentially caused by the inference of multiple signals produced by the minute distribution of targets within each resolution cell. In simpler terms, speckle noise in an image represents the presence of salt and pepper type noise, where some pixels are highly illuminated and others are very dark, occurring in granular salt and pepper patterns. In the context of noising model, adding speckle noise to an image might involve multiplying the intensity of each pixel by a random value drawn from a certain distribution, often a Gaussian distribution. This can make the model more robust to such noise in the real world. Both types of noise are common in real world situations, and training models to handle them can be very beneficial for their performance on real world tasks. Now, let us look at the code that we are going to use for noising model, and we are going to start with Gaussian noise model. The code structure is very similar to the one that we have followed earlier. We read the image, we then convert the image to grayscale, and we then resize the image. Okay. We then apply the Gaussian noise model through these 3 lines of code. The rest of the code is for displaying the original image and the changed image. And we also display a histogram that will correspond to the original and the resultant image. That's what the rest of the code does, and we are accomplishing this through the help of matplotlib.pyplot. Okay, the core set of codes that we are using in Gaussian noise model is these 3 lines of code. This line generates Gaussian noise. The numpy.random.normal function draws random sample from a normal or Gaussian distribution. The first argument is the mean of the distribution, second argument is the standard deviation, and the third argument is the number of samples you want to draw. In this case, it is generating samples which equals the total number of pixels in the grayscale image from a normal distribution with a mean of 0 and a standard deviation of 1. Each sample represents noise for a single pixel. The second line that you see here, this helps to reshape the one-dimensional Gaussian noise array GN into the same shape as the image img underscore gray. So if img underscore gray is a 100 by 100 pixel image, GN will become a 100 by 100 matrix where each element represents noise for a corresponding pixel in img underscore gray. The astype uint8 function is converting the data type of GN to 8-bit unsigned integer format. This is the standard format for images where pixel intensities range from 0, which is black, to 255, which is white. The third line that you see here, this adds the Gaussian noise GN to the grayscale image on a pixel by pixel basis to generate a noisy image. CV2.add is used instead of the normal addition operator plus because it performs saturated arithmetic. That is, if the result of an addition operation is greater than 255, it will be clipped to 255 instead of overflowing. So in summary, these lines of code are generating a noisy version of a grayscale image by adding Gaussian noise to it. So after the addition, we see the original image and adjusted image. As you can see, there is quite a bit of noise in this image, and we are seeing that in the resultant histogram as well. We will use these 3 lines of code when we want to use speckle noise. The expression that you see here is different from the expression here. The expression here would not add Gaussian noise in the same way as this expression. Instead, it performs a different operation entirely. This expression would not add Gaussian noise in the same way as this expression. Instead, it performs a different operation entirely. img underscore gray into GN performs element-wise multiplication of the grayscale image and the Gaussian noise. This operation modifies the intensity of each pixel in the image based on the corresponding Gaussian noise value. As a result, this operation amplifies the pixel intensities rather than adding noise to them. If you want to add noise to the image, it is more common to add the noise directly to the pixel as we see here rather than this particular option. Now we will look at denoising models. Denoising models often use filters to remove noise from images. The type of filter used depends on the type of noise present in the image. Let's start with Gaussian filtering. Gaussian filtering is often used to blur an image or to reduce detail and noise. It works by convolving the image with a Gaussian function. The result is a smooth blur that looks very natural to the human eye because the pixels in the image are averaged with their neighbors in a way that nearer pixels influence the average more than the distant ones. Gaussian filters are often used in reducing Gaussian noise and are also used for achieving a smoothing effect in an image to reduce details. Due to the nature of the Gaussian function, the filtering effect preserves the edges in the image since the intensity change across edges is gradual and not abrupt. The next one is average or mean filter. The average or mean filter works by moving through the image pixel by pixel, replacing each value with the average value of neighboring pixels, including itself. This neighborhood is usually square, like 3 by 3, 5 by 5, or 9 by 9 that you see on your screen. The average filter is a simple and intuitive filter that is often used for general noise reduction. However, it tends not to preserve edges very well. The larger the neighborhood, the more an edge gets blurred in the output. Last but not the least is the median filter. The median filter is a non-linear digital filtering technique often used to remove noise from an image or signal. Like the mean filter, the median filter considers each pixel in the image in turn and looks at its nearby neighbors to decide whether or not it is representative of its surroundings. Instead of simply replacing the pixel value with the mean of neighboring pixel values, it replaces it with the median of those values. The median is much less sensitive than the mean to extreme values or outliers. Therefore, the median filter is much better at preserving sharp edges while removing noise, and it is particularly effective at removing salt and pepper type noise. Each of these filters has its own strengths and weaknesses, and choice of filter depends on the specific task, specific image, and the specific type of noise you are trying to remove. Now, let us look at the code for the Gaussian based denoising model. As in the previous scenarios, we are first going to read the image, convert it into grayscale, and then resize. Before that, we import the necessary libraries. The core set of codes for denoising is these two lines of code. The rest of the codes are for displaying the image side by side, that is the original and the resultant image, and the associated histogram. Let me zoom the core set of codes that we are using for denoising. Let me zoom it. This code generates Gaussian kernel of size 3 and standard deviation of 0.9. This code applies the generated kernel onto the image. We can see the original and the resultant image, and the adjusted image, we can clearly see the noise has been removed. And this is depicted in the histogram as well. The histogram is a plot of pixel values and frequency. If we use averaging based denoising filter, we need to adjust the code. Here, W is equal to 5 indicates the window size. This sets the window size for the averaging filter to 5. This means that the kernel will be a 5 by 5 matrix. The next one that you see here, this line creates a 5 by 5 matrix filled with ones and then divides every element by 25, the total number of elements. This gives a 5 by 5 matrix where each element is 0.04. When this kernel is applied to an image, it effectively calculates the average of every 5 by 5 block of pixel. The next line applies the averaging filter to the image. The filter operation effectively replaces every pixel in the image with the average value of its 5 by 5 neighborhood based on the kernel, thereby smoothing the image. This kind of averaging filter can be very effective for reducing high frequency noise in an image. However, it also tends to blur edges and other high frequency details, so it is often used as a simple first pass noise reduction step before applying more sophisticated noise reduction algorithm. Instead of this one, we can also use the median blur. Before that, let's see the original and the adjusted image. The adjusted image is now free from much of the noise. Okay. Now coming to the median filter, instead of average, we use median. Median is free from exposure or impact to outlier and extreme values. I need to adjust the code with this. The function cv2.median blur applies a median blur to an image. The median blur operation replaces each pixel's value with median value of the pixels in its neighborhood. The earlier one used mean, now we are using median. So the size of this neighborhood is specified by the second argument to the function. This line applies a median blur to the image using a 5 by 5 pixel neighborhood. For each pixel in the image, it looks at the 5 by 5 block of pixels centered on that pixel, sorts these 25 pixel values because we need to sort in the case of median, and replaces the original pixel value with a median of these 25 values. This operation, that is the one using the median, is particularly effective at removing salt and pepper noise, which corresponds to random occurrences of black and white pixels. Unlike an averaging filter or Gaussian blur, a median blur can preserve edges in an image, since median is not affected by few extreme values. Always remember this. As a result, if a pixel is on an edge, so that some of its neighborhood is on a bright region and some is on a dark region, the median is likely to be a value from the edge and not the bright or dark region.